Hello everyone, welcome to Civil Engineering and Stuff. And in today's video lecture, we will be discussing about Kennedy's theory for the design of regime channel. Now, this term regime channel we have discussed in detail in the previous video where we have discussed the basic criteria for a stable channel. So, if you want to understand in detail, you can watch that video lecture. For the sake of understanding, we are going to discuss first what regime channel is, and then we will discuss the Kennedy's theory for the design of regime channel. Now, a regime channel, in a simplest term, a regime channel is nothing but a stable channel. A regime channel is nothing but a stable channel. And what is a stable channel? A stable channel is a one where there is neither silting nor scoring. There is neither silting phenomena taking place nor scoring phenomena taking place. Silting again is a process or a condition where there is accumulation of sediment particles in a riverbed, while erosion of these sediment particles is what we call as the scoring. Now, in a regime channel, what we want is we do not want this silting and scoring phenomena. This means that the water that is flowing in a regime channel, the water that is flowing in a regime channel has enough velocity to let the particle which are in suspended state to remain in the same state, and the particles which are at rest, that is the bed particles which are at rest, should remain at rest. So this condition is what we call as the regime channel. The particle which are in suspended state will remain in that state, and the particle which are at rest will remain in that state. So there will be neither silting nor scoring phenomena, and that is what we call as the regime channel. And basically, there are two famous theories, the Kennedy's theory and the Lacey's theory, which have proposed their own conditions and criteria and design step for the design of this regime channel. And that is what we are going to discuss in the subsequent lecture. In this video lecture, we are discussing about the Kennedy's theory, and in this lecture, we are going to discuss only the theoretical aspect of the Kennedy's theory. That is what the Kennedy suggested, what are the design steps, what are its limitations. The numericals related to Kennedy's theory we will discuss in the next lecture. All right, so let's start with the discussion over the Kennedy's theory. Now, Kennedy's theory, as the name suggests, it was proposed by Mr. Kennedy, who was an executive engineer deputed in the Punjab PWD department. And basically, based upon his own experience, he understood what are the criterias that are required for a channel to be in regime state. And based upon his experience, he did some observations and gave some design steps. So these study that Mr. Kennedy did was done in Upper Bari Doab Canal System, which is generally the part of UP and Uttarakhand at present. And based upon this, he suggested that the silt supporting power of a channel depends upon the generation of eddies from the base of channel. Now, this means that like he did a lot of observation, and he said that what, in an irrigation channel, like in an irrigation channel, there is water flowing. In an irrigation channel, there is water flowing, and because of the flow of the water, there are the eddies that are generated at the bottom of the channel section. There are eddies that are generated at the bottom or the base of the channel sections, and these eddies are the reason because of which the silting phenomena and the scoring phenomena take place. The eddies are generated at the base. Okay, these eddies are nothing but the ripples, kind of ripples that are formed because of the movement of the water, and these ripples causes the silting and scoring phenomena. So he said the reason for the generation of these eddies is the friction between the base of the channel and the moving water. This is the water that is there. So the friction between the moving water and the base of the channel results into the generation of these eddies. So this is the main thing that he identified through his observation and through his study. So he said, since the eddies which are generated due to the friction between the moving water and the riverbed, uh, if we minimize the generation of these eddies, we can control the silting and scoring phenomena, and basically through this we can, if we control this silting, if we control this generation of eddies, we will control the silting and scoring phenomena, and hence the channel will automatically achieve a regime state. So he said, what if what if the velocity of the flow, if we control the velocity of the flow in an irrigation channel to such an extent that this velocity is sufficient to keep sediment in the suspended state. If the water that is flowing in this irrigation channel, if we control the velocity to a certain such an extent that it ensures that the velocity of the flow is sufficient to keep the sediment in the suspended state, then there won't be any deposition of the sediment. Hence, we will avoid the silting behavior or the silting phenomena. Likewise, if the velocity is again controlled to such an extent that velocity is not very high, so there won't be erosion of the riverbed. So scoring will also be avoided. Alright. So he said we have to control the flow of the water. We have to control the velocity of the flow such that the particles which are in suspended state will remain in suspended state, so the deposition of the particle will not take place, and hence the silting will be avoided. Likewise, the velocity we have to control in such a way that it is not high enough to take the sediment particle of the riverbed with it, and hence this scoring will be avoided. So that was the whole gist of the Kennedy. This is what Kennedy said, that we have to control the velocity of the flow of the water that is flowing in an irrigation canal. And if we are able to do so, we will achieve a regime state for the channel section. We will achieve a regime state for the channel, for that specific channel. So that is what the foundation for the proposal for Kennedy was. He gave certain design steps to control, to find out that specific velocity for us, for that specific channel, so that there will neither be there will neither be silting, there will neither be silting nor scoring, neither silting nor scoring. And to do so, he did an assumption. The assumption was that the sediments in a riverbed are of incoherent in nature and are discrete in nature. This assumption basically helps to assess each and individual particle, the behavior of a particle individually. Okay, that is the whole purpose of assuming that the particle or the sediments of the riverbed are incoherent and discrete. Very important point. You should remember this. Okay, this was the assumption. All right. So taking this as the foundation, he Mr. Kennedy did a lot of investigation and proposed his own design step for a regime channel. What were the design steps? The first step was to assume a trial depth. We are discussing now the design step proposed by Kennedy for a regime channel. So Kennedy said, for a channel to be in regime state, I will propose you certain design steps. What are the design steps? These are the design steps that we are discussing right now. He said to assume a trial depth, and using that trial depth, find out a velocity. Using that trial depth, find out a velocity, and the formula of that velocity I am giving you. Okay, I am giving the formula to find out the velocity using what? Using a trial depth y. What was the formula given by Mr. Kennedy? Formula was as the velocity v naught is equals to 0.55 m into y to the power 0.64. This was the formula given by Mr. Kennedy. Kennedy gave the formula that we have to assume a trial depth and use, but after assuming a trial depth, you find out a velocity by the formula that I am giving to you. The formula is v naught is equal to 0.55 m y to the power 0.64. What is m? M, again, Mr. Kennedy defined the m as the critical velocity ratio, which is the ratio between the actual velocity and the velocity that we get after assuming the trial depth. After assuming the trial depth. So your m is the critical velocity ratio, which is the ratio between the actual velocity v to the v naught, the velocity that we get after assuming the trial depth. And this v naught is what we call as the critical velocity. Candy said that this is the critical velocity. So your m, the critical velocity ratio, is the ratio between the actual velocity to the critical velocity. Okay. Now, the value of m, Mr. Kennedy said that the value of m depends upon the type and the size of silt grade. It depends upon the type and size of silt grade. And he said, based upon my experience, I am giving you the value of m. The value of m will be equal to 1 for river particles of northwest India in Sindh and Punjab region. The value of m can be taken as 1 to 1.2 for the particles of the river in South India, that is the coastal particle, and can be taken in between 0.7 to 1 for fine particle derived from the lower value of Indus and Ganga plain. That is, if you are constructing an irrigation canal in southern part of India, you can take the value of m between 1 to 1.2. If you are constructing an irrigation canal in the Indus and Ganga plain, take the value in between 0.7 to 1. And take the value m equal to 1 if you are constructing the irrigation canal in northwest India in Sindh and Punjab region. He said that. And these value I am giving you based upon my experience. He was an executive engineer. He said, based upon my experience, I have deduced these values. All right. So this was the value. So this was the first step. First step was assume a trial depth. Based upon the trial depth, find out a critical velocity. Formula for critical velocity again given by Kennedy, which was equals to 0.55 m y to the power 0.64. M was the critical velocity ratio, which was the ratio between actual velocity to critical velocity. Done. First step done. Then he said, once you find out the critical velocity, find out the area of that irrigation canal. How you will find? Using A equals to Q by V naught, very basic relationship. Now, any irrigation canal is to be designed for a given discharge value, right? So discharge we know. So in the previous step, we had to find out the value V naught, that is the critical velocity. So through that, we have find out the area. Then, assuming a side slope, if not given, assuming a side slope of, let's say, any side slope, you can assume n horizontal is to 1 vertical. Now, generally, half horizontal is to 1 vertical is the like generalized side slope that is taken. So we can take half horizontal is to 1 vertical if not given. We can design a trapezoidal section. If not given, we'll go for trapezoidal section, and it can be triangular, circular, depending upon the case, but generally trapezoidal section is there. So we have to find out the dimension of a channel by assuming it to be a trapezoidal section having a side slope of half horizontal is to 1 vertical. And using that side slope value, we have to find out the value of B. How we are going to do? You will understand it in much better way once we do the numerical. But the third step for now, just understand that we have to assume a side slope that which will be n horizontal is to 1 vertical if not given. So generally it is taken as half horizontal is to 1 vertical, and the section that we are going to design is trapezoidal section, and through that we are going to find out the parameters. We are going to find out the a value using the formula a equals to b plus ny into y, which is the formula to find out the area of a trapezoidal section. Parameter p equals to b plus 2y under root n square plus 1. Through this we are going to find out the width also, as well as the a value we have already found in the previous one. We'll also find out the parameter value. Okay. Now, once we have find out the area in step 2, once we have find out the parameter in step 3, we have to find out the we have to find out the fourth step is to find out the hydraulic mean depth, which is R is equals to A by P. Again, simple formula, generalized formula we have used multiple times. R equals to A by P. Using this formula, we have to find out the hydraulic mean depth. We have to find out the hydraulic mean depth. Now, up till point 4, up till fourth point, if we look the basis of this up till this point is the assumed trial depth through which we have found out the critical velocity. So we have a critical velocity value. Now Mr. Kennedy said that once we have found out all the parameters, through the value R, through the hydraulic mean depth value that we have found in the fourth step, using this value of R, you have to find out the actual velocity. You have to find out the actual velocity of the irrigation canal. Now, to find out the actual velocity, you can use the Cutter's equation, Manning's equations, Chazy's equations, whatever you want. But Kennedy said that it's better. I'll recommend Cutter's equation. Okay, Kennedy said I am recommending Cutter's equation, but you can use anyone. You can use Cutter's equation, Manning's equation, Chazy's equation, whatever you want. But I'm recommending it's better to use Cutter's equation. So using Cutter's equation, like Kennedy said, and based upon his design step, he's saying that I am recommending Cutter's. So with folded hands, we'll go for the Cutter's equations. Okay. So he said using Cutter's equation, find out the actual velocities, and the Cutter's equation is V equals to 23 plus 0.00155 by S. S is the bed slope. S is the bed slope. Usually it is given in the question. Okay, S is the bed slope plus 1 by N. N is the side slope, divided by 1 plus 23 plus 0.00155 by S, again the bed slope, bracket close, divided by the side slope N, divided by under root R. R is the hydraulic mean depth into under root RS. Again hydraulic mean depth, S is the bed slope. So through this we are going to find out the actual velocity. Okay, through this we are going to find out the actual velocity. If you are going to use the Manning's equation, you can use this V equals to 1 by n R to the power 2 by 3 S to the power 1 by 2. Okay, no issues. But Kennedy recommended that go for Chazy's or Cutter's formula. He said that it's better to use Cutter's formula, but you can use anything. Okay, so it's a very important point again. So through this, now if you observe what we have done, we have assumed a trial depth through which we have found out the critical velocity, and through the critical velocity we have found out the area of the irrigation channel. Through this, we have found out the width as well as the parameter of the irrigation channel. We have found out the hydraulic mean depth of the irrigation channel, and from there we have found out the actual velocity. Okay, so the next step or the final step in which the Kennedy said was, see, we have found out the critical velocity V naught and we have found out the actual velocity V. Now, this critical velocity and actual velocity should be equal. This V naught value should be equals to V value. Okay, and generally up to two decimal places the value should match. That is x dot y value up to two decimal places the value should match. Okay, so he said that we have find out the critical velocity and we have find out the actual velocity, and both the values should be equal. A general reference or general provision is that up to two decimal places the value should match. Okay, so V should be equals to V naught. If that is the case, then our depth is okay. If not, then we have to assume a neutral depth. If not, we have to assume a neutral depth and we have to repeat the whole process. So this was your design step for Kennedy's theory. I again in a very quick way going to repeat. The first was we assumed a trial depth. Through a trial depth, we went for critical velocity. To find out the critical velocity, again he gave his own formula. V naught equal to 0.55 m y to the power 0.64. M was the critical velocity ratio, the values of which he again gave based upon his experience. Then through the after assuming the trial depth, we find out the critical velocity through which we find out the area of the irrigation channel. Assuming we are designing a trapezoidal section, we assume a side slope, and through this we find out the parameter as well as the width of the channel. Then we find out the hydraulic mean depth, and after finding out the hydraulic mean depth, we find out the actual velocity using Cutter's equation. And at the end, both should be equal. V naught should be equals to V at least up to the two decimal places. If that is okay, then our design is good. If not, then we have to assume the neutral depth. If V naught is not equals to V, then we have to assume a neutral depth. Okay. Now there are certain guidelines for the design of Kennedy's theory. These guidelines are framed so as to have a it becomes easy to assume a trial depth and the design becomes less laborious. So if you have a discharge value in between 0 to 20 cumac, assume a depth of 1 meter. This is cumac. This is meter. Okay. Likewise, if the discharge is in between 20 to 40 cumac, the depth will be 2, 40 to 82.5, 80 to 100, 3 meters, and if it is greater than 100 cumac, then the depth will be 3.5 meters. A general provision for a channel bottom slope, if not given, should be 1 by 3500 to 1 by 5000. Where it will be used? It will be used here, okay, to find out the actual velocity. If not given, then this is the provision or the range of the channel bed slope or the bottom slope to be taken. If you are going for Manning's n and it is not given, then this is the range of Manning's n that is to be taken for the different channel sections. For good earthen channel section, it should be between 0.022 to 0.0255. Likewise, for these and these, the values are given if you are going for the Manning's n. Okay, done. So these are certain guidelines. All right. So there are certain like we have discussed so far the design steps and certain guidelines. Now let us discuss the limitations of Kennedy's theory. Certain limitations through Kennedy's theory. What are the limitations? Let's discuss those. So the first and the prominent limitation of Kennedy's theory was that according to Kennedy, eddies are generated from base of the channel. However, in real practice, eddies are generated from the sides of the channel also. Sides of the channel also. This means in the starting of the lecture we discussed that Mr. Kennedy said that there are eddies that are generated at the riverbed, because of which this silting and scoring phenomena takes place. The reason for generation of these eddies, the reason for generation of these eddies was the velocity of flow of water, velocity of flow of water. Now, because of the velocity of the flow of water, there is a friction. There is a friction between the bed slope as well as the moving water. Okay, now you see the water is flowing in the channel whose boundary is the side slope as well as the bed slope. So definitely the moving water will have friction at the side slope also, right? The moving water will also have friction at the side slope also along with the bed slope, correct? So definitely eddies will be generated from the sides also. Eddies should also be generated from the side also. So silting and scoring phenomena can be there at the side slope also. Large and small, we are not talking about that. We are talking only about the generation of eddies. The basic, there are eddies that are generated at the bed slope. The reason was the friction between the movement of water or the velocity or the flow of the water and the bed slope, and because of which the eddies were generated. So if this is the case, then eddies should also be generated from the side slope also. All right. So this was one of the prominent limitation of Kennedy, that he didn't consider the eddies that are generated from this side slope. Okay. The second limitation was that he has not given his own formula to find out the actual mean velocity, but has used Cutter's equation or Manning's equation. As we have seen in these steps here, to find out the actual velocity, he said to use Cutter's equation or Manning's equation. So all the limitations and assumptions that are applicable for Cutter's or the Manning's equations are also applicable for this Kennedy's theory. Understood? I'll again repeat. We have seen that to find out the actual velocity, very easily Mr. Kennedy said that to go and use Cutter's equation or Manning's equation. So definitely for Cutter's equation and Manning's equations are formulated based upon certain assumptions. So all the assumptions and limitations that are applicable for these two equations are also applicable for Kennedy's. That is again a limitation, that he has not given his own formula to find out the actual mean velocity. The third limitation was that he gave the value of m in a very arbitrary way. The value of m was given in an arbitrary way and was arbitrarily related to the silt grade without giving a proper relationship. Okay, again, like the value of m, there was no proper justification, but he said that based upon my experience, I'm telling you. Okay, so because of the lack of proper justification, this is again a limitation of Kennedy's theory. Then he has not given his own equation to find out the channel bottom slope. Again, either it is given or like a range is given. You have to take in between the range and then you have to design. Okay, so this is again a limitation, that he has not given his own equation to find out the channel bottom slope. Then he has not taken into consideration the silt concentration and the bed load. This means that they like he didn't assume the diameter of the silt particles into consideration. You see, let's say the velocity is same for two different channel sections. One is having smaller particle and one is having bigger diameter silt particles. So you can very well assume that very well understand that this velocity of flow of the water can easily take these smaller diameter silt particles with them compared to these coarser particles. Okay, so these diameter of the silt particles and the concentration of the silt particles plays a very important role. So that assumption was also not that parameter was also not included by Mr. Kennedy. So this again became his limitation. And then like no importance was given to the width to depth ratio. There was no mentioning regarding the maintaining the overall aspect ratio of the channel sections. Not considered by Kennedy. So this was again a form of limitation that was there in the Kennedy's theory. So these limitations was was covered by the theories that was proposed by Lacies in his design step for regime channel. So Lacies theory basically covered all these limitations, and we are going to discuss about Lacies theory in the subsequent lectures. Okay. One important point regarding Kennedy's theory, which really comes as an objective in various competitive exams, is that the Garrett diagram can also be used to find the channel dimensions by Kennedy's theory graphically. So the Garrett diagrams can be used in Kennedy's theory. Okay, these are like the graphs that are plotted based upon the observation, and this can be used to find out the different dimensions to design a regime channel. Okay, just an important point. Just remember that in for your objective purposes. All right, so this is all the theoretical aspect of Kennedy's theory. I hope the lecture was clear to you, and if you have still so far, this means that like you found the lecture useful and interesting. Okay, so kindly like the video and subscribe to the channel for more videos like this, and post your views in the comment section. If you have any doubt regarding any of these steps or any of the parameter that is not clear to you, you can always ask in the comment section. In the upcoming lecture, we are going to do certain numericals on this Kennedy theory. Okay, so keep a watch for that. Press the bell icon so that you get a regular notification as and when a lecture is uploaded. Thank you for watching. Have a very nice day.